Hi, everybody. Thanks for the invitation. This is actually joint work with my student Visheki Maya and my collaborator Alex Volfosky. So the good news is that I couldn't have really asked for a better talk before mine because I'm also talking about stochastic block model. And kind of the overarching motivation I want to make is that stochastic block model arises as a model for network inference problems. Right? There's a lot of work where people are looking at networks and trying to make sense of them. Is there some type of structure in it? Is this structure meaningful? Can you find this structure? And in some sense, the stochastic block model is like the simplest, non-trivial model you could think of for such structure. So kind of in the number of people working in it, I would say there's a huge area where people actually look at networks and try and do things. There's an area on the other side, kind of in information theory, where we are studying these thresholds on things like the symmetric or the two-community stochastic block model. There's some area in the middle where people in statistics are looking at more flexible models for network, but there's not a lot of flow between these different ends of the spectrum. So I think I'm just putting this up there to acknowledge that first off, there's kind of a gap between kind of the thresholds and the things we might like to look at in the models we know how to study, and the types of problems that maybe people that are really working out on network inference might be interested in. And so kind of one of the goals or the motivation behind this talk is to slowly push from the right a little bit more to the left. Left a little bit more to the right. OK. Nope, right to the left. One way or the other. All right, so in large friendly letters, same as Jean, right? We have a G. This is our observation. This is a graph. This is a network, or you can just think of it as an adjacency matrix of our network. And X. These are going to be labels associated with the vertices. And one kind of basic question is how much do we learn? This is a question of, what do we know after looking at the graph as opposed to before? And there's also a question of if we want to make estimates, how well, is a given procedure and estimating the ground truth. So kind of information theoretic or estimation theoretic. So I think this is almost exactly the same list of papers that Jean may have had on his slide previously. So the point is there's been a lot of recent work in this by a lot of folks really figuring out some of the particulars, especially of the symmetric stochastic block model. So this is, again, like Jean showed you, I'm giving you the opportunity to try and find the community structure yourself first. So again, in a real-world situation, you might not know how many clusters there are. You might not know much about them. I'll tell you there's 3 clusters here, right? And your job is to sort the rows and columns. I'll save you the time, right? And so here we have 3 community stochastic block model. Now, how do I represent this? Well, again, kind of the information we want are labels. So these are just, they could be anything. They could be names, colors, right, numbers. But it's going to be useful to embed them into a Euclidean space. And this is so we can start thinking about the geometry of the problem. And so for a symmetric one, if you have kind of k points, I can just associate them in k-1 dimensions as the points on some of the the boundaries of some type of polytope, right? So in 2 communities, I just have +1 or -1. As I go up higher, I need a few more dimensions. And without loss of generality, I can just normalize these so that they have mean 0 and identity covariance. And why this is useful is because it basically says the inner product between these representations is one of 2 numbers, right? If we're in the same community, we get a large positive number. If we're in different communities, we get a negative number. So this representation allows me to kind of turn this, if you want, geometry into just saying 2 points, 2 different numbers if we're in the same community or different community. And then based on this, I can construct, this is going to be called the K-community symmetric stochastic block model. And the relevant parameter here is that there's some signal strength R. So if R is 0, there's no information. The graph has nothing to do with the underlying truth. R is positive. People in the same community are more likely to be friends. R is negative, the other way around. D is the expected degree of the node. So much like Jean, I'm going to be looking in the situation where D is increasing at some rate. So the dense setting where the size of the network is going to grow, and D is going to grow. The only difference between this setting and what Jean did is that Jean also allowed these xi's to be non-equal probabilities. But this, in the case here, the difference is that you can have more than just 2 communities. So there's this really nice work by Deshpande and Abe and Montanari where they kind of characterize the limit of the mutual information, right? So it's a simpler form of the result Jean was just showing. And what I think is important here is there's kind of 2 trivial upper bounds, and this mutual information actually matches that first upper bound up to this magical point 1. And kind of via IMSE relations, this actually tells you something about the estimation theoretic question. It's saying up into that magical point 1, your MSE is trivial. It's what you would have gotten without seeing the graph at all, and it's only at that magical point that your MSE starts to go down. So this is kind of what we call the weak detection threshold. And so there's, within the regimes, there's a lot of work saying where exactly does this happen? Well, it's 1 here. But there's also a lot of work, in exact recovery, almost exact recovery, where you're out at this tail, and so your signal strength is growing. And it's a lot of the work actually in the statistical literature where they're giving guarantees, these are consistency type guarantees, and those are all going to require being a regime where your signal strength is growing, and the questions they're asking is does your uncertainty go to 0 in those scaling regimes? But here we're kind of scaling up in the interesting one, well, an interesting one. All right, how is this represented? Well, as Jean alluded to, there's this connection with the signal plus noise problem, or a Gaussian noise problem. And now we're in higher dimensions. So really, it's I think about as we have these centers here, these are kind of our representation of the labels. And we can think about a problem where we observed a noisy observation of the label in this space. So now you're seeing it actually does kind of matter how I choose the representation of these points. But this is kind of the connection that's been done in the previous work, saying, OK, you can think about the signal plus noise problem. And of course, here, the quality of inference is quantified by this number S, the SNR. And so if you have a very low SNR setting, we immediately see, OK, there's a large overlap between the supports of these kind of Gaussian mixtures. It might be difficult to dissociate between the different clusters. Or in high SNR, it becomes much easier. And another fact about this problem is that it's essentially just a kind of a low-dimensional problem that you can actually characterize performance measures of. So I can actually just compute kind of numerically what is the MSE, or the optimal performance in this problem, this estimation problem. OK, so here's our first result. And I guess what I should say is this is more or less a modest extension of kind of what people have done previously in the case of k equals 2 communities to k communities. Right? And again, the idea is that you have some formula where your formula depends on the top. This is somehow a parameter of your signal plus noise problem. It's easy. This is a very friendly-looking term, easy. You find a minimizer of this with respect to the SNR. So this S is here, and then S is also in this, the definition of Y. Once you found that minimizer, you then turn to that signal plus noise problem, plug it in with that SNR, and that tells you your performance. So this is, if you want, the highlight, or the takeaway is that if you have a symmetric stochastic block model, or if you have a 2-community asymmetric stochastic block, as we've just seen, then effectively thinking about the signal plus noise problem with this kind of single scalar SNR tells you your fundamental performance. OK, so the question is, what happens when we want to look at something a bit more, a little less simple? And that is, we have kind of more communities, but there could be different interactions between different individuals in the community. I think not all networks in the world are symmetric stochastic block models. So the particular model we're going to look at here, well, here's an example. Again, it's unsorted. Can you sort it? This is an example of a degree-balanced stochastic block model. So there's no longer the assumption that the size of the communities are the same. And also, there's no longer the assumption that we have only a single interaction within and between communities. So here, kind of every between community pair gets a different potential interaction. The only constraint here is that we're degree balanced. And what that means is that each row, right, so each row corresponds to an individual, has the same expected degree. And the reason it's degree balanced is if you're not degree balanced, it turns out to be really easy to find communities just by looking at the degrees. So we're going to say there's no information just in the degree. You're going to have to go a bit further. Okay? So this is a more general class of stochastic block models. So how do we analyze this? And how do we kind of get a characterization like it's been done previously in the literature? So the first thing I'm going to talk about is the representation of our labels. Right? As I said before, I can embed them in a Euclidean space. I'm going to do the same thing here, but I'm going to embed them in such a way. Right now they have unequal probabilities, but I'm going to preserve the rule that they have mean zero and identity covariance. So there's not a unique way to represent them this way, but there's always a way to do it. And so what that means, right, is that maybe community labels labels associated with communities that are more likely are going to be closer to the origin, whereas rare ones are going to be further away to balance it out. So this is a choice of representation. Next, I need to think about, well, how are we going to generate the stochastic block model? So the general stochastic block model allows a matrix of, there's k by k possible interaction terms. Here, the only difference is before I had a single number r that characterized the strength of relationships. And now I'm going to replace that by a matrix. So this is a k-1 by k-1 symmetric matrix. Again, if this matrix is 0, there's no structure. And I could say things like if it's positive definite, this is assortative. If it's negative definite, it's disassortative. But it could be indefinite. So we could have both assortative, disassortative structures. There's no kind of rule about how you have to choose it. Right? So this is a very general setup. And again, the D just controls the average degree. So the only differences now is I have non-uniform supports. So my points are different. And then I have this matrix R. So how do we what's the corresponding signal plus noise problem here? And I guess before we look at that, let's think about, well, what is it even we want to measure, right? If I had a symmetric stochastic block model, I know that my error for each, it doesn't matter which community I'm in, a single number can summarize my performance. But if I have multiple communities with different behaviors, it could be the case that I can identify some relationships in some communities, but not others. So I need a multivariate performance metric that tells me about pairwise performance. And to do that, I'm going to look at this thing we'll call the MMSE matrix, which is just the expected conditional covariance of the community labels averaged over the individuals. And just to keep in mind, if you just simply take the trace of this matrix, this is the standard measure of performance that people have been looking at in weak recovery. But if you look at the diagonals or the off diagonals, it has other information. And I think the key idea here is that the equivalent signal plus noise problem is one that's characterized effectively by one that no longer has an isotropic noise. Right? You need to think about something that has, so there's two ways of saying it. Either you have a noise covariance, or as I like to think about it, is you have a matrix signal to noise ratio. So here it's parameterized by a positive definite matrix S that tells you both the strength and the direction of the noise in your model. So here we have two possible cases. One where we see that depending on how the covariance or the noise is shaped, we're going to be able to find or not see different types of relationships. Again, the emphasis is that this problem, though a bit complicated before, this is just a Gaussian mixture model. Right? I just have means. My means are defined by my prior on the communities. And then I have a covariance, the same covariance for every community, and that's defined by this matrix S. And again, you could compute this matrix. It's a bit more work, but this is not inherently a high-dimensional problem. This is analyzable. So our main result, as I've set it up, essentially says that you have now the similar basic idea. You have some function, depends now as a multivariate parameter, this positive definite matrix S of S and Rs. You find the minimizer of this. You take that minimizer, you plug it into the signal plus noise problem, and what we show is that's going to give you an upper bound on the MMSE. Okay, so, and this is an asymptotic upper bound. In order for this to be tight, we need to show a corresponding lower bound. All right, so one thing you can do with this is you can get some pictures of what's actually going on, right, and how do you have some these asymmetries in the network. So here's an example where the communities, there's 3 uniform communities, but you're changing the eigenvalues in that R matrix. So you're changing the types of connection behaviors that you see. And what we've overlaid here is the black are contour lines predicted by the theory, whereas the red is the heat map obtained by running belief propagation on networks. So a limitation of belief propagation is that it doesn't work well with large average degrees. So it's actually a degree equals 10, even though our theory says D has to go to infinity, but it gives a good qualitative description. And we see this square here, this 1, this is this special threshold where certain algorithms are known to work well once you're outside of the square. We can also go to an asymmetric one. So just like Jean was talking about in the case of 2 communities with asymmetry, what you get is this region where essentially, and this is what this blue line indicates up here, there's a hard region. So this is a case where in principle, so in fact we've shown that the MSE is less than the trivial amount in this region, but it's inside the square, meaning there's no known efficient algorithms that can succeed here. Right? And again, this the existence of a hard phase transition needed some asymmetry in our problem setup to arise. I'll also note that there's a correct qualitative behavior here, but the exact match between the formulas and the results gets worse at the outskirts. And that's, again, not surprising given that you need the degree to grow for the theory. Okay, so if there's a few steps in the proof, you've seen some of the key ideas in what Jean presented, which was really nice. So the key, I guess, difference, one is that from the beginning is to harness a very general non-asymptotic relationship. And that is if we just think about this signal plus noise problem characterized by this positive definite matrix. And then I say, well, what happens if I take my mutual information between my labels in the graph as well as the side information, and I take the gradient with respect to this matrix SNR and evaluate that at 0, that's exactly the quantity I want, my MMSE matrix. So this is, I said, it's very general. This holds for any kind of joint distribution on G and X. It's really not relying on there being a communities or finiteness or anything. Okay? So once we're going to use this as our starting point, and then the question is, can I evaluate this mutual information with both G and Y, and then just take the gradient of the final formula? You have to be a bit more careful. But that's the basic idea. So it's kind of sidestepping a bunch of issues about how do you go from mutual information to estimation performance by doing it directly from the beginning. The second step is exactly what Jean alluded to before, the idea of channel universality. We showed that the mutual information is very similar to that. Had instead of we seen this graph model, we'd seen something under Gaussian noise. So then the main technical problem is how do we kind of go from this, kind of as a matrix estimation problem to the signal plus noise problem. And so this is what I have here. Y is signal plus noise. Z is Gaussian noise. And I think one of the kind of new innovations of our proof technique is to really get a very, very general upper bound on this just by noticing inequality of the gradients with respect to the two parameters. And so that is you can compare the gradient with respect to the single scalar parameter in the matrix problem to the gradient with respect to the mutual information, I mean with respect to the matrix SNR in the signal plus noise problem. And once you have this, I mean, it plugs in and you get something, there's no kind of little O-terms floating around anymore, and you have an exact bound. And using that exact bound, we're able to then get our upper bound on the MMSE. So I guess in conclusion, you know, a main takeaway from this, I think the insight is that if you want to understand the geometry a bit more, this is an example of a problem where when you're looking at the very simple cases, a single number is enough. Right? A single number summarizes performance, and a single number summarizes your effective kind of model that you're going to use to analyze it. But when you're going to start looking at more kind of multivariate problems with different types of interactions, you need multivariate measure of performance, and you need a multivariate interpolation parameter. But many of the ideas kind of go through at the same level. I also think that there's a lot of connection here, which I didn't get a chance to talk about, which is actually what people do in practice is they might do a spectral method. And when you do kind of spectral clustering, you actually see in the decomposition what comes out is something that looks like a Gaussian mixture model. And in fact, we can relate our kind of Gaussian mixture models obtained here to what you see in spectral clustering, especially in high SNR regimes. It converges to kind of known asymptotic theory there as well. So I think that there's hope that this will help inform practice on some of these problems, maybe to some extent. All right, I think that's all.